There we go. Okay. Well, here's how maybe you guys had some thoughts. Anybody have any thoughts about how many ways this could occur? How many ways could he make 3 of 5 throws? How many? 60's wrong, but it's where are you getting that idea from? How many? Why 60?
Well, I just tried using the.
Ah, so you did 3 per 5 permute 3? Close. It's 5. It's pretty close to that. That's very so you were calculating this. It's actually 5 choose 3. But 10 is correct. It just didn't seem like enough, I guess, right? Okay, but it is more than 5, right? So let's talk about. So why did you say 5 choose 3?
Because there's 5 different. So, I also don't know.
Okay, let me think. Let me see if I can. So you're saying, right? Yeah, yeah, that's yes. But now we did say that we're finding different orders, so it does seem a little weird. But let me just with the combinations. Let me just try to make you wise combinations and not permutations, right? So here's the idea, right? So you can think of a word, right? So if he's making exactly 5 of his, right? One possibility would be this, right? So notice you can think of this as you can number the shots, right? So this permutate, this could be represented by 2, 3, 5, right? That's one way to do it, right? Another way to do it would be 1, 4, 5, right? So we are choosing 3 of these 5 slots to have Y's in them, right? And the remaining one have N's in them, correct? We see that, right? Now it's a combination because choosing 1, 4, and 5 is the same as choosing 5, 1, and 4, right? So we are, think about it, right? I could have 5 index cards, right, in a little bag, right, with the numbers 1, 2, 3, 4, and 5 on them. I could pull out 3 of those index cards, right? That would, those 3 numbers associated would correspond to a specific shot order that are made, right? 3 of the 5. And if I pulled out 1, 5, and then 4 out of the bag, one at a time, it would be the same thing if I pulled them out in different orders because it still the numbers refer to the position of the shot, right? So that's exactly right. So this is 5, choose 3, right? And notice before it was 5, choose 4, which is actually 4, right? So the answer is 5, choose 3. If you use the formula, this is 5 factorial divided by 3 factorial, 2 factorial. Everyone remember that for the combinations? So that's 5 times 4 factorial times 3 factorial over 3 factorial times 2 times 1, right? These 3 factorials cancel out. I have 5 times 4 divided by 2, which is 10. You want to convince yourself, try to spell out all the words, right? You will find 10 of them if you try hard enough. If you find more, I don't know what you did. You did you listed some things there twice. Yes. Permutations is that the order matters. And it seems like the order matters here, but we're just choosing. So we are deciding on an order. But when we decide the order 1, 4, 5, that'd be the same as decide, right? Making the first, fourth, and fifth is the same as making the fifth, fourth, and the first, which is weird because you're choosing. It's what order you choose the order in, right? Like there's a double order thing going on there, so that can make it a little bit more complicated. So there are 10 ways, right? And each of those 10 ways are equally likely, so we only need to find the probability of one of those, right? So the probability of making, so then this is what I think Mars was thinking about, okay? So the probability of making the first 3 shots, right? The probability of making a shot is 0.75, right? And what should I exponentiate that to with power? 3, right? Because there's 3 of those. And if I make 3, I must be missing 2. So the probability of making them exactly in that order is about 3.4%, but there are 10 different ways, right? Each of those ways having a 3.4%. So the probability, oh yeah, so that's 10 times that. So that's roughly 34%. So notice, right, we can kind of generalize this, right? There's really only 3 numbers here, right? There's the probability that in any particular trial it will be successful, right? In this case, that's the probability he makes a shot, right? That's 0.75 here. There is how many total trials are occurring, and then there is how many of the trials are successful, right? Those are the only 3 things you need to know for a binomial distribution. So we just need some notation for representing all of it, which is on the next slide, and then this will give us the formula in a little bit. So there's more things here, right? You don't need to get this. So they write P of S. I don't think I'm going to write that again. P just means the probability of a success, right? So in the previous example, that P was, so I'm not saying P always equals this number. This is from the last example. Everyone following? I'm going to write more on this. Right? So 1 minus P is the probability of a failure, right? So we can, sometimes we designate that with Q. If you don't like having to remember Q, you can just write 1 minus P. It's the same thing, right? So in this case, Q, the probability of a failure. So that would be Q in this case, right? The probability of a failure, right? And P plus Q is always equal to 1. Therefore, 1 minus P is equal to Q, right? N is the fixed number of trials, which was, in the last example, so I was doing something a particular number of times. Yeah, so that's 5, right? So what it means fixed number is you could play a game where you could say, Drippy's going to shoot free throws until he makes 3, right? Sometimes that could happen in 3 trials. Sometimes it could take 10. Theoretically, it could take 30, right? That's not a fixed number. So in a binomial, that would not be a binomial. So in a binomial, fixed number of trials is n, right? So n in the previous situation is 5. That's n, the number of trials, right? That's really all we got to focus on, right? And then x is the number of successes we're interested in, right? So in the previous slide, that was 3. And then before that, we had x equals 4. And boom, there's a lot here, but just remember, n is the number of trials, x is the number of successes, q is the probability of p is the probability of a single success. That's all you really need to get out of this slide, all right? That brings us to this as our special formula. So our probability, so just remember, right? N, number of trials, right? P is prob of success. X is number of successes. You can also, if you want, right, notice it says 1 minus P. This is the same thing as Q. I will go through how to use this formula. Let's just notice some things by definition, right? If there are n trials and x of them are successes, right? Sorry, x of them are successes, the remaining must be failures. So that would be n minus x, right? There are 20 trials and 5 are successes. 20 minus 5, 15 are failures, right? So let's just go through this. So in the Drippy example, there were 5 trials, right? the probability of success in any given trial was 57%, which as a decimal is 0.57. And we did 3 and we also did 4, but the most recent time we did 3, so let's stick with x being 3. So then using this formula, the probability that x, the number of successes, was exactly 3 was equal to, you just use this formula, right? This is the important formula. This is the one you need to have written down or memorized, and just get the intuition from it. It is n. N, everybody, again, is 5. Choose 3. That's what x is. P to the x, which again is 3. 1 minus p, right? That's 1 minus p. We found that's equal to q, which in this case is 0.43, right? 1 minus. And 5 minus x, 3 is equal to 2. Notice, using this formula, this comes up with the exact same probability, the exact same form that I got from before. The exact same form, and we can see, I could have just given this formula, I could have not done any of the stuff I did for the last 20 minutes, right? I could have just given you this formula, but you would have no idea what the hell it meant or why it worked. It would have just been magic. But let's just look at this here, right? Assuming that not all of the trials are successes or all failures, there's different ways that it can occur. There's some ordering that occurs, right? Everyone following me? This is the number of orderings, right? Number of ways I can arrange those 3 successful free throws and the 2 unsuccessful ones. All right. Now, each of those outcomes are as likely to occur. So, okay, I make 3 in a row, then miss the next 2, right? That's one of the outcomes. I multiply by the number of ways I could arrange that. That'll get my total probability, right? So this formula will work for any situation that is binomial, right? So when you're answering questions, your strategy is first, is it binomial, right? When you're asking, is it binomial, you're thinking about these 4 things. Fixed number of trials, right? So 5, for example, only 2 possible outcomes, success and failure, right? Sometimes, right, just remember that that's defined more broadly, right? As long as the 2 outcomes, right, have specific probabilities, it's okay, right? So like imagine the Drippy game. That's technically a binomial experiment. Not just technically, it is, right? Even though the failure, there's 5 ways that can happen, well, they're all equally likely. So you can just say success 1/6, failure 5/6, right? Students have trouble with that one more than this one, but you can think there are different ways Drippy could make or miss a shot, right? You could just chuck it, right, and totally miss the backboard. It could spin around, right? There are different ways, but we know the prop. But there's, as far as we're concerned, there's 2 ways, right? The probability for each trial is constant. In this case, it's 57%, right? Bobby doesn't buy that that's how it would actually work, but this is an approximation, right? Because we're assuming that the trials are independent. Questions on how to use this formula? All right, let's just do some examples. So you find the formula, determine if it's binomial, then you divide n, p, and x, and you just plug that bad boy in, right? And it's going to work out really well. All right, so let's do an example. It's a little bit depressing if you use various. So this is the formula right here, right? It's not that hard to memorize. What? Yeah. Because, right, we can reason through it. You came up, you don't need to memorize. If you just remember what it's coming from, right, it's easy to memorize because you came up with this formula on your own. Well, maybe not on your own. I guided you towards it, right? So let's consider this, right? %38 of Americans who are working, right, say that they are very satisfied with their job. At least back in 2016. Maybe that's, I'm going to guess that that's less now just because that's just my guess. All right. So I randomly pick 4 employees. And we want to find out the probability that exactly 6, I randomly picked 6. I want to find out the probability that exactly 4 were satisfied. Is this an example of a binomial experiment? Fixed number of trials. Six are being chosen. And fixed number of successes. Yep, and that's 4 in this case, right? And there are only 2 outcomes. Very satisfied or not. See, there's also different ways you could be not very satisfied. You could be somewhat satisfied or very unsatisfied, right? But as far as this problem is considering, there's only 2. Now, technically speaking, it says that I'm choosing 6, right? If I choose Regina right now, she can't be chosen again. So if she's very satisfied, now the probability slightly is less than 38%. But this is what I was saying, right? If you are choosing less than 5% of your sample, we can assume that even though you've picked somebody out, it doesn't change things enough, right? So this is, right, technically, right, we would have to be choosing with replacement. But with replacement, without replacement, doesn't matter when you're choosing from all employees in America and you're only choosing 6 of them. Does everyone follow what I'm saying? We can treat this as if they're independent. So the answer for is binomial is yes. So then all we have to do no. P stands for probability. So we're looking from a number from 1 to 0. So P is okay, those other numbers you got though. So N, the number of trials, Regina, is 6. N is the big number. So N is the total number of trials. X is the number of successful trials. Right? Then you just need to plug this into the formula. So it starts with N. 6 choose 4. Times 0.8 to the power of 4. 1 minus P, that would be 0.62, right? And this exponent would be 2, 6 minus 4. Right? And then you can see how this comes, right? There are 6 choose 4 ways to order the happy employees in with the non-happy ones, right? Since there are 4 of them that are very satisfied. And then, right, so that's the number of ways. And then, like, say, consider all the probability that the first 4 employees will be very satisfied, multiply 0.38 by itself 4 times. The second 2 not satisfied, multiply 6.2 by itself twice, right? So that would just be if there was only one way to order, I wouldn't worry about the 64. This comes in for the number of ways you can order it, right? So you could just type that in your calculator. You could also do a little bit of work on your own here, right? This is 6 factorial over 4 factorial 2 factorial. Which I believe is 15. Set this in, you get roughly 0.12. So roughly 12%. I'm going to just write that here because I know something else is coming there. All right. Still binomial for B? It's the same story. All I'm doing is changing the number of satisfied employees, right? I'm going to give you a hint. All of these things are the same except one of them. What is the one that's different? So that is which of the 3 variables? X. The X is no longer 4, it is now. Yeah, all 6 are very satisfied. Correct, absolutely. All right, so now using this formula, it would be 6, 6, and this is a little weird. You wouldn't actually necessarily need it. This reduces pretty easily. What's the exponent of 0.32 going to be? So 0. So I guess if it was 0.32, it wouldn't matter either way. Any number to the 0 is 1. Notice this number would equal 0 otherwise. Notice 6 choose 6. I have 6 books. How many ways can I choose 6 of them? Right? This is equal to 1. Notice, and anything to the 0 is 1. That's weird, but it has to be because this is not a, otherwise this would be a 0 probability, right, Mars? So notice this is the same thing as 0.6. So we actually would have known this. I could have done this with the drippy thing. It wouldn't have been very interesting though, right? If all of them are very satisfied, there's only one way that can happen. Person 1 sat, right, etc. Right? And I only need to multiply by the probability that each person's satisfied, and I don't need to worry about this part because each of them, there's 0 of these people, right? So it's good to notice that this we could have done this one probably without this formula, right? But good thing to notice that it reduces it to the simpler case where everyone's on the same page. It reduces to the same thing that you would have thought, right? Just multiply the probability of each success. So, and you do that, you get 0.003, which is depressing, right? Most of you are probably employed of some kind. Imagine 5 of your coworkers. The probability that all 6 of you are very satisfied with your job is 3 in 1,000. That shit's sad, man. All right, so letter of the story, do well in college, you're more likely to be satisfied with your job because it will probably involve dealing with fewer people. One point to notice, when you are changing, when you're doing the same scenario, but you're asking different parts, the value of X often changes while the other numbers